All right, today we're cracking open the chemist's toolkit. We're going to see how some of the most basic, most important molecules on Earth are actually put together from the ground up. So let's dive right in. You probably don't think about it, but you're interacting with hydrocarbons all the time. I mean, the fuel in your car, the gas you cook with, all that stuff. They are, and I mean this literally, the engine that runs our modern world. So what are these things anyway? Well, the name kind of gives it away, right? Hydrocarbons. They're just compounds made of hydrogen and carbon atoms. That's it. Super simple ingredients. But man, can they build some incredibly different things. Okay, so this hydrocarbon family, it's got a few different branches, each with its own, personality. We're going to start with the simplest, most stable members of the group. Yeah, you've got your alkanes, alkenes, alkynes, even fancier stuff like benzene. But for today, we're going to really focus on the bedrock, the foundation of the family, the alkanes. And this is where it gets kind of cool, because you can't just, throw some carbon and hydrogen in a beaker and get an alkane. Nope, there's a bit of a puzzle we need to figure out first. So alkanes are known for being super stable, like really stable. Their old school name, paraffins, actually means less reactive. And that's because all their carbon atoms are locked together with these super strong single bonds. They're just happy. They're content. They really, really don't want to react with anything. So that brings up a pretty big question, doesn't it? If these things are so stubborn, so unreactive, how in the world do chemists even make them in the first place? Well, that's where the cleverness comes in. Chemists have a whole toolbox full of tricks to get the job done. Now, there are a bunch of ways to make alkanes, but we're going to look at two really powerful and totally different strategies. Okay, method number 1. This is all about addition. I like to call it the saturation station. The whole idea is take a molecule that's a bit unstable and, well, complete it. The official name for this is catalytic hydrogenation. Basically, we start with what's called an unsaturated hydrocarbon. Think of it like this. It's got double or triple bonds, which means it has empty spots where more hydrogen could go. It's unsaturated. So we just add hydrogen. We fill up all those empty spots until every bond is a single bond, and bam, you've got a fully saturated, stable alkane. But here's the thing, this reaction doesn't just happen by itself. You need a helper, a crucial ingredient called a catalyst. This is usually a metal, think nickel, palladium, or platinum, and it acts just like a workbench or maybe a landing strip. It grabs onto the reactants and holds them in just the right position so they can actually connect. So let's zoom in and see what's happening. First, the hydrogen gas molecules land on that metal workbench and they break apart into individual atoms. Then, the unsaturated molecule comes along and those hydrogen atoms just hop right off the metal and onto the carbon chain. And here's the really cool part. They always attach from the same side. It's a specific move called syn addition. All right, so let's recap hydrogenation real quick. It's a surface reaction, right? It all happens on that catalyst. The hydrogens add from the same side, that's syn addition. It gives off heat, which is a big clue that you're making something super stable. And the whole reason it works is that the catalyst lowers the energy needed to get the reaction started. Simple as that. Okay, on to method 2, and this one is a totally different game. Forget adding stuff to a molecule. Now we're going to stick 2 molecules together with some molecular glue. This is what we call a coupling reaction. You can really think of it like chemical welding. You take 2 smaller, identical parts, and you just fuse them together to make one bigger, perfectly symmetrical molecule. The name for this one is the Wurtz reaction. Here's how it goes. You start with 2 identical molecules called alkyl halides. That's just a fancy way of saying an alkane that has something like chlorine or bromine struck to it. Then, you use some sodium metal in a special solvent, dry ether, to basically stitch them together. And what you get is always a longer alkane, it's always symmetrical, and it always has an even number of carbons. So how does this glue work? Well, first, that super reactive sodium metal literally throws an electron at the alkyl halide. This snaps a bond and creates this crazy reactive thing called a free radical. It's super unstable. So what happens? 2 of these unstable free radicals find each other and they immediately slam together and form a new stable bond. And just like that, you have your new, longer alkane. Okay, a few key things you gotta remember about the Wurtz reaction. The star of the show, the thing in the middle, is that free radical. Also, because you're always sticking at least 2 pieces together, you can never make methane, the little 1-carbon alkane. Just can't be done this way.
It is perfect for making symmetrical alkanes, but if you want something lopsided, not so much. Oh, and that dry ether? It's absolutely crucial. It's there to stop the sodium from going wild and reacting with, everything else in the room.
So there you have it. Two totally different ways to build the same kind of molecule. Which brings us right back to where we started, the chemist's toolkit. Let's put them head to head. Catalytic hydrogenation, that's an addition reaction. You've got a framework, and you're just filling in the gaps with hydrogen. The Wirtz reaction, on the other hand, is a coupling reaction. You're actually building a bigger framework by sticking two smaller ones together. They start with different things, they work in different ways, and they're good for different jobs. And really, that is the whole point. This is the heart of what chemists do. Building molecules isn't just random mixing, it's a strategy game. It's about looking at what you want to make and then picking the perfect tool to make it. Yeah, I think this really sums up how a chemist has to think. There's no single best way to do something, there's only the right tool for the job you're trying to do. It all comes down to your strategy. Do you already have the carbon backbone you want? Then you're going to use addition to fill it out. Do you need to build a bigger, symmetrical backbone from smaller pieces? Then coupling is your go-to move. They're just two different roads that lead to the same destination. When you think about it, from our fuels to plastics to life-saving medicines, chemists are basically architects, but on a molecular scale. And strategies just like these are the fundamental techniques they use to build the very stuff our world is made of. It really makes you wonder, doesn't it? What are they going to build next?